In this video, I'll be going over the slides related to superposition of waves. And here right away on this first slide, we can kind of see what the whole idea is really about. You see a pulse traveling from left to right, or maybe you can't see it. I always forget that like my camera is going to be sort of up here on one side of the slides there. I don't know if that fixes it, which I can't see as I record this. I just sort of see the screen in front of me. So my apologies if, I think in the last video I was pointing something out, and when I looked at it afterwards, I said, oh, well, yeah, they could still deduce the essential ideas there. In any case, here we see that the wave that's traveling from left to right and the wave that's traveling from right to left with a lower amplitude, they're going to eventually meet or superpose. And so the principle of superposition just says add up the individual displacements of each wave and you'll get the resultant displacement. And so in green here, you see the resultant wave. It's just the sum of the lower amplitude wave here that's going from right to left and the higher amplitude wave, the one that's going from left to right. When they meet in the middle there, they sort of add up, and then each pulse passes by and they go about their way. So when waves meet, we add them up. That's really at the heart of the principle of superposition. The learning outcomes associated with this are to explain and use the principle of superposition of waves, explain experiments that show diffraction and interference, and solve problems involving two-slit and multiple slit interference. Each one of these learning outcomes really leads to the next one. So once we can apply the principle of superposition of waves, for example, with coherent waves, well, then we're going to get these points of reinforcement and cancellation where the waves are, adding up to become stronger and reinforced, or they're adding up in such a way where they're going to destroy each other, and that's destructive interference. So we can account for an interference pattern by thinking about the principle of superposition. And here we see solve problems involving two-slit and multiple slit interference. So the Young's double slit experiment that was first done in the early 1800s really showed interference with light. And because interference was a phenomenon that's really associated with waves, it led physicists on this path of thinking about light as a wave, which light indeed exhibits wave-like properties, but light is a little bit more difficult to understand than just thinking about it as just like, a water wave, for example. Explain and use the principle of superposition of waves. And so here we have sort of like a good textbook definition of principle of superposition. When two or more waves meet at a point, the resultant displacement is the algebraic sum of the displacements of the individual waves. And if we apply that principle of superposition to, say, two waves that meet and each wave is in phase, and so we see with the example here, the constructive interference, each wave begins by sort of rising up above equilibrium. And so when this trough meets this trough, we get a double trough, right? The combined wave gives us constructive interference. We're building up, we're constructing the wave bigger. But if the waves are 180 degrees out of phase, right, like we see with the destructive interference example, then by the time, say, this first wave, which begins by sort of going below the equilibrium position, it gets to a trough, it's going to add up with the wave that was 180 degrees out of phase with it. In other words, this wave down here is kind of beginning at that point, right? 180 degrees out of phase, or half a wave, length later. So the path difference between those waves is half a wavelength. That will always lead to destructive interference when the path difference is half a wavelength, or when the phase difference is 180 degrees, because we're adding up a trough with a crest, and that just adds up to 0. So at each point along the resultant, we just see that those waves wipe each other out. They cancel out. Therefore, they're destroying each other, and that's destructive interference. And each type of interference is really the result of just applying the principle of superposition. We're just adding up the waves and seeing what the result is. If the result is reinforcement, if the result is cancellation, and if we see a repeated pattern of reinforcement and cancellation, then that's an interference pattern. Here's some key definitions for the vocabulary here. Explain experiments that show diffraction interference. So what is diffraction? It's the spreading of a wave as it passes through a gap or around an edge. Interference is the formation of points of cancellation and reinforcement where two coherent waves pass through each other. And then constructive interference occurs when two waves reinforce to give increased amplitude. Destructive interference occurs when two waves cancel to give reduced amplitude. If a wave passes through a gap, it's going to spread out. But if the gap is pretty wide, that diffraction, the spreading of a wave, isn't a big effect. And so we hardly see any spreading for this example here, where the gap is very wide compared to the wavelength of the wavelength being the distance from blue line to blue line, each one of those being like a plane wave passing. If the size of the gap is about the same size, or ideally the same size as the wavelength, that's where we maximize the diffraction effect. We get the most spreading of the wave as it passes through that gap. And so that is one wave phenomenon. Waves diffract. They spread as they pass through a gap or around an edge. You can see in this bottom figure here that the wave is also spreading out as it passes around this edge here. Explain experiments that show diffraction and interference. Here I provided a link to a really cool old-timey science movie that really explains this well and shows this. And I just kind of like the video itself. So the double slit experiment is where we're ensuring coherence because we're using the same wave source. And so if we send the same wave source through two slits, then at each slit the waves are going to spread out, and as they spread, there's going to be a place or a region where the two spread out waves will overlap. They meet, they superpose. And we can clearly see on this figure on the right here where we have two waves, each one emanating from the respective gap there, are meeting, and we see these places where crest is meeting trough, and at each point along these lines here is a point of destructive interference where the waves have just basically canceled out. And in between those points, like here where I'm putting these points, those would be where crest is meeting crest, and we're seeing sort of, maximum displacement, constructive interference. But here we basically can observe the destructive interference by inspection. We see where the waves have basically canceled out. And so that pattern there is the characteristic interference pattern. And the double slit or a two slit experiment really is the famous example of interference. This slide is also reinforcing the same idea. Minimum, crest meets trough, so we're going to get destructive interference. A maximum is where crest meets crest, and that pattern repeats itself. That repeating pattern of reinforcement and cancellation is interference. And having a double slit is one way to ensure the coherent wave sources. If the waves are not coherent, they're still going to, the places where the waves meet will still apply the principle of superposition. We just want to observe that pattern of at this distance away we get maxima, minima. It'll just be sort of more random where the points add up because the waves are going in and out of phase with each other as one wave might be changing its frequency. But if the waves are coherent, meaning they have a constant phase difference, then they're always going to kind of meet up half a wavelength later, and we'll always observe that pattern. The other thing to keep in mind about two waves being generated by a source is that if one of the sources, even if the frequency is coherent, but one of the sources has a much higher amplitude, then the interference pattern also won't be as noticeable because the effect of the larger amplitude is going to basically flood the calculation. the effect of the smaller amplitude won't be so much, it won't be noticeable, it's basically negligible. So if each amplitude is about the same, then the interference effect is more noticeable. You see twice the amplitude, for example. But if one is already much larger compared to the other one, then by adding that smaller amplitude to it, it doesn't really create a big effect there. Here we see a monochromatic light source, the light of one color, and then the double slit experiment, and the interference pattern would only be observed where the waves meet, right? There might be places where the wave is spread out and the other wave either hasn't had a chance to make it there or never will because of sort of the geometry. Another slide showing the same thing. This one experiment, which has been designed to contain all the mystery of quantum mechanics, is a quote from my all-time favorite physicist, Richard Feynman. Here's a book that was written about the a whole bunch of the versions of the two-slit experiment through two doors at once, the elegant experiment that captures the enigma of our quantum reality. Kind of see the image there. All right. When we first introduced these slides, we just had an inquiry lab, and I think I've since uploaded a video that kind of explains that inquiry lab and a follow-up video that's more structured related to two-slit interference, which brings us right into solve problems involving two-slit and multiple slit interference. Where the waves have traveled half a wavelength longer, where one wave has traveled half a wavelength longer than another wave, we're going to observe destructive interference. All right. Now, if we look at the slide here, you see how the crest of this wave is where the trough of this wave is, and so by the time they meet up, they're canceling each other out. Whereas these two waves here are meeting crest to crest, trough to trough, and so we're getting that constructive interference example there. And it really just depends on how much further did one wave have to go compared to the next one. And so on this slide, we can kind of see how this point is like here, where we would observe the destructive interference. So it's a little bit lower than this brighter spot. This distance, all right, corresponds to how much longer this wave has had to travel. If the wave has had to travel a half a wavelength longer than its neighboring wave, then it's going to be 180 degrees out of phase, like we see over with the destructive interference example. But if the path difference is an integer multiple of the wavelength, so even though this wave still had to go longer to get to this point, it just had to go an entire wavelength longer. And so it's still going to have a constant phase difference where it's meeting, crest to crest, trough to trough. Every point of the wave is meeting sort of in sync with its neighboring wave. And so you see how these ideas build upon one another. Some key terms for us to be mindful of. Coherence. Two sources are coherent when they emit waves with a constant phase difference, right? That means their frequency is the same and it remains the same over time. Interference is the formation of points of cancellation and reinforcement where two coherent waves pass through each other. I think we've seen that before. Diffraction, again, is just to reinforce this, the spreading of a wave when it passes through a gap or past the edge of an object. Phase difference is the difference in the phases of two oscillating particles expressed in degrees or radians. So an entire wave has 360 degrees or 2 pi radians, and so we can kind of look at where within the wave cycle are we, or where are the waves meeting? Is it half a cycle, a quarter of a cycle, 90 degrees, pi radians, 180 degrees, and so on, to express when the waves meet each other, what's the sort of shift? How far is one off from the other one, just in terms of a waveform? The path difference is the actual difference in the distance traveled, by two waves from coherent sources to a particular point. So, and if that path difference is an integer multiple, then we know that the wave and the sources are coherent. Then we know that we're going to get constructive interference. If the path difference is half of a wavelength, which would mean the phase difference is 180 degrees or pi radians, then we're going to get the destructive interference because crest would be meeting trough. And the principle of superposition, again, is when two or more waves meet at a point, the resultant displacement is the algebraic sum of the displacements of the individual waves. Coherent sources emit waves that have a constant phase difference. This means frequency is the same and remains constant. These two waves are coherent. They have a phase difference, which is constant over time. Although we probably would get that with a light bulb like it shows here, but at least the figure there, they're showing this as a constant phase difference. Here's more realistic. We have incoherent light, so the incandescent light is sort of putting light out of all the different colors, and it's white. Whereas a laser is one frequency, so it's coherent light. In order to use a laser and get interference, we typically will use a single laser and pass it through a double slit, because lasers can have this sudden change of phase. The laser light kind of comes out in packets is kind of one way to think about it. And so there might be like this sudden phase shift in the waveform. And then, we can kind of think about the wave pattern repeating. Any sudden phase shift in a laser would be shared at sort of the same moment if we're using a single laser source. And so that's why we use, instead of using like two green lasers to try to interfere them, we'd use a single laser and pass it through a double slit, or more likely a diffraction grating, which is multiple slit interference. And the physics is much the same. So the same thing is happening where the waves are meeting up and reinforcing, and we're observing that interference pattern. This is another slide to show interference. So if the waves are in phase, we can see that the waveforms match there. We get constructive interference, but if they're 180 degrees out of phase, or pi radians out of phase, or half a cycle out of phase, then we're going to get destructive interference, and the resultant is just nothing. Another slide showing diffraction. The narrow slit, or narrow as compared to the size of the wave. The wavelength is about the same as the width of the gap, then the diffraction effect is most pronounced. Get two slits, we're going to get some interference because those coherent waves are going to meet, and we'll get that pattern, reinforcement and cancellation. This is showing a little bit more mathematically that idea of a path difference of one wavelength equals a phase difference of 0. This leads to constructive interference. All right, so if the path difference is some integer multiple, here m, any whole number of the wavelength, right? That's the difference in the path. If that's equal to one whole wavelength, two whole wavelengths, some whole number, then we get constructive interference. But if it's some number plus a half times the wavelength, so 1.5, 2.5, 3.5, and so on, if the path difference is, that, then we're going to get destructive interference. We could also think about it in terms of phase difference, okay? So the phase 2 pi times the change in sort of the path divided by the wavelength, that would give us the phase difference in radians, because we're using, 2 pi radians. Or 360 degrees would be what we would do to solve it for degrees. So the difference in phase is the change in the path divided by the wavelength times 360, right? So it's sort of like the path difference divided by the wavelength. It's that sort of ratio times either 2 pi or times 360 degrees. Path difference divided by the wavelength times 2 pi gives you the radians. The path difference divided by the wavelength times 360 gives you the phase difference in degrees. Two slit and multiple slit interference, being able to solve problems. There are many worked examples that I have previously uploaded that are specific to this. So we use the equation lambda equals ax over d in order to solve two slit interference, where lambda is the wavelength And A is going to be the distance between the slits. X is the distance between sort of the points where we observe the interference, and so the distance, say, if it's light waves, between bright spot and bright spot, or the distance between dark spot and dark spot. And D is the distance between where the slits are and where we're observing them. And so it's really all just sort of geometry, and you know, that idea of path difference is really key there. We're just looking at how much longer has one wave had to travel compared to the other one, and everywhere where the waves are meeting and that path difference is an integer multiple of the wavelength, we get those points of reinforcement, you know, bright spots for light wave. And here all of the variables are defined there, and you see what's hopefully a more familiar figure up here. For diffraction grating, we have multiple slit interference, and so now we're allowing the light to pass through multiple slits, and at each slit the light's going to spread out, and so we're going to get the same interference pattern, but it's going to be a little bit sharper because we're sort of getting more waves to interfere there. And so it's usually preferable in the laboratory to use a diffraction grating rather than like a two slit, because you're going to get a little bit more better results. Take a look at the link to the worked examples belonging to multiple slit interference and diffraction grating equations. Really good key ideas on this slide. Sine theta can never be greater than 1, so there's a limit to the number of spectra that can be obtained. That's n, the order number. The equation d sine theta equals n lambda, where d is the distance between the slits in our diffraction grating, theta is the angle to get to that maximum, and n is the number of maxima. So it's the integer number to the next bright fringe. So if we're solving, say, like how many maxima will be observed, then we're going to maximize sine theta, make it 1 for a given wavelength, for a given diffraction grating with a known distance between the slits. We could solve for how many order we'll see sort of relative to the 0 order, which is always directly across from the two, or from the diffraction grating. Take a look at the worked examples that I've done with those. White light dispersion is when we have white light incident upon a diffraction grating. We're going to effectively split apart the white light into all of its different colors there, all the different frequencies of the visible spectra. Because violet light has the shortest wavelength, it is diffracted to the shallowest angle theta. So thinking again about the equation here, if d is constant and n is, say, the first order, so we're just looking at the first order for all of the different frequencies, then we are diffracting all of those different wavelengths or frequencies of light to a different angle theta. And the shallowest angle, or the lowest angle, will be the one with the shortest wavelength out of violet. So red is diffracted to the steepest angle theta, where violet is diffracted to the shallowest angle, and the number of order that we would observe would be dependent upon everything that's sort of in this equation here, right? Namely the distance between the slits. How many lines do we have, like, per meter in our diffraction grating? This is one of the ways that the data can be presented to us, the number of slits per meter, n, and then we could calculate d as the inverse of that, right? So if we know that there is, for example, I think in the worked example that you can see here, there are 500 lines per millimeter, that's n, and so we do a quick calculation to say, well, what is d then, the distance in meters between the slits? The diffraction grating has lines with space between them equal to d. Lambda is the wavelength of light, n is the order number, and theta is the angle. And then here is a sort of a slide about a famous version of the double slit experiment, the delayed choice quantum eraser experiment. Says it still lacks a proper explanation. So take a look at that and see if you can try to figure that one out. Till next time.